Welcome to the Lean NPI webinar. I'm Julian Coates and will be taking you through the Lean NPI flow based on our latest software releases, a solution that brings better NPI results both for you as a designer and your manufacturing suppliers. First, what do we mean by new product introduction in the context of PCB design and manufacturing? The essential point is the transition from the design domain where, regardless of the type of design software being used, the primary focus is creating the model of the product, to the manufacturing domain where the main focus is defining and running a suitable manufacturing process that results in high quality, lowest cost production. Between these two domains of product definition and manufacturing process execution stands the NPI stage, comprising the product NPI stage, where the designer's product is validated as being compatible with the intended manufacturing processes, and the process NPI stage, where the precise manufacturing process for a particular product is defined, including the creation of all execution-ready documents and programs for use on the factory floor. During this seminar, we will summarize the essentials of DFM and its significance for the designer. Then we will explain our recommended best practice for the most efficient way to hand off a product design into the manufacturing process, a method we call Lean NPI that works in the context of any PCB design flow. Which naturally leads us to show starting the flow with the application of DFM as a process that is truly concurrent with laying out the PCB, followed by comprehensive preparation of the manufacturing level product model data for the fastest and most automated introduction into manufacturing process preparation. If you are a PCB designer, you will recognize some or all of these challenges. How do you manage the handoff to prototype manufacturing? Do you get working prototype boards into your hands fast enough and built as you intended? When you switch from prototype to volume production, are unexpected engineering changes required? Do you get the same product as you got from the prototype manufacturer before? How to take more control over manufacturability at the design stage without having to be a deep domain expert in manufacturing processes. Before we move ahead with the Lean NPI flow, let's take a few minutes to look in a little more depth at the traditional NPI flow that you have probably experienced or observed in the past. You may recognize some of the steps from your own situation. The roles are divided between the design organization, the ultimate owner of the product definition, and the various manufacturing organizations. Here we first show the prototype PCB fabricator. The roles may be integrated within the same organization or distributed across independent companies, depending on the degree of manufacturing outsourcing. The designer lays out the PCB and then generates the traditional set of documents and data files for delivery to the prototype fabricator, who then reintegrates all that data back into a single product model in the CAM system. Often at this stage there are requests for further information from the manufacturer who wants to be absolutely sure that he is working from a complete and correct model of your product. Following any necessary clarifications, the fabricator will run a DFM analysis of your product, which may give rise to requests for engineering changes so as to achieve acceptable manufacturability. This in turn gives rise to another set of documents and drawings for reintegration in the CAM system, and, assuming no further clarifications or engineering changes are required, the fabricator can make final verification with you that he has entered data from your drawings correctly. For example, if an assembly panel drawing has been issued, after which process preparation for fabrication can proceed, and in parallel the data and documentation for assembly can be compiled and delivered to the assembly NPI department. Then begins a similar sequence with the assembly NPI engineer, during which the product model will be reintegrated on the assembly side, this time including integration of the bill of materials and approved vendors list, and following any necessary clarification and engineering change cycles, the NPI assembly engineer can proceed with process preparation. As the project moves from the prototype stage to volume production, additional manufacturing service providers will go through similar cycles of product model reintegration, DFM analysis followed by requesting engineering changes, which not only causes further delay and cost escalation, but also the risks to quality increase as a result of so much product model reintegration work taking place at the manufacturing level. The result of running such an NPI process across multiple manufacturing suppliers can be unwelcome delays and cost increases, coming from the multiple clarification and engineering change cycles, made worse by the inherent quality risk associated with the extensive and inevitably variable product model reintegration work taking place across your manufacturing supply chain. Maybe some or all of that is familiar to you. Before we move on, it is probably worth asking yourself what some of the key metrics are within your own NPI process. For example, how much time do you spend answering questions from the manufacturers, and how much time do they spend working out which questions to ask? How many design revision spins or engineering changes do you go through when your product is already handed off to a manufacturer? The industry average for companies who do not use DFM analysis at the design level when last surveyed was 2.8 revision spins per design. By contrast, here is a more integrated NPI process. In fact, mentors recommended best practice NPI flow for any combination of CAD and CAM systems. A key aspect of the recommended NPI flow is the left shifting of DFM analysis rules to a unified product-level NPI function in the design organization, running concurrently with the PCB design operations. The NPI engineers in fabrication and assembly, who manage their DFM rules in relation to their manufacturing processes, feed their rules to the NPI specialist at the design level, who manages them for use concurrently within the layout process. The result is the preparation of a single integrated ODB++ product model ready for final verification and handoff to the fabrication and assembly NPI departments. Because the product model has been prepared using the manufacturing process rules of the manufacturers, the frequency of delays due to the need for clarifications and engineering changes is reduced. You as a designer get your product manufactured faster and more exactly according to your requirements, and the manufacturers can focus their resources on their core competence of preparing and running the manufacturing process. Indeed, this lean NPI process flow scales across multiple manufacturers, thus accelerating not just the prototype phase, but also the transition into successful volume manufacturing. Key aspects of the flow are verifying at the design stage that the product is manufacturable by all your suppliers with acceptable first-pass yield and cost, followed by handoff of a single integrated product model to the manufacturing process engineers for consistent process NPI by any or all of your approved suppliers. The lean NPI solution, when added to your design flow, comprises two essential aspects. The first aspect is the maximum left shifting of DFM analysis into the PCB layout process. It is a generally accepted rule that the time and cost impact of identifying the need for and implementing an engineering change to a product design increases by 10 times with every step taken in the life cycle of the product, from design to NPI, prototype, and then volume manufacturing. Thus, identifying and implementing engineering changes early in the product life cycle can bring substantial cost and time savings in the course of bringing a new product to the market. The same independent survey that identified an average of 2.8 manufacturing-related revision spins in the traditional flow revealed that design organizations who implement a lean NPI flow can expect a 57% average reduction in such engineering changes, with a reasonable expectation of reducing it still further. By gathering the rules from manufacturing and applying them during your PCB layout process, regardless of the layout software vendor, you will experience a new level of total cost reduction and speed in the successful launch of your products. But of course, It has to be easy for the PCB designer to do, along with all the other concurrent tasks he has to handle. In the next few minutes we will run through in more detail what we mean by manufacturing rules and how easy they are to apply concurrently during design. The second aspect of Lean NPI is the use of intelligent integrated product model data for handoff to the process NPI stage. By preparing a single product model that is DFM validated and does not require integration by the manufacturers, a range of benefits is achieved in the NPI stage, including time savings in both product and process NPI stages, a reduction in the risk of mistakes and misunderstandings, and higher consistency of product across multiple manufacturing suppliers. The probability that you will get the product you intend will increase if you take full control of the product model in your own NPI operations, rather than leaving it to each manufacturer to define for themselves based on how they interpret multiple files and documents. During this webinar, we will be looking more closely at the version 8 ODB++ and its full scope for supporting a more automated NPI flow. But first, let's take a closer look at DFM and the best practice for maximizing the left shift. The key point about DFM analysis is that the rules to be applied should relate to the manufacturing processes that will be used when manufacturing the PCB. This is why DFM is not the same as the application of design rules, which relate to the product design more than the manufacturing process. Examples of manufacturing processes are, for fabrication, the drilling process, etching, component placement, reflow, and test. There are many additional processes to consider, but when taken together from your prototype and volume manufacturers, you are in a strong position to left shift DFM into your design flow. After applying the manufacturing process rules to the model of your PCB, the manufacturing process risks are presented back to you according to their severity and the manufacturing process that has a compatibility problem with the product as currently designed. Notice that the DFM analysis rules are not presented as go-no-go, like design rules checking. Manufacturing process is all about percentage yield and degrees of quality and product reliability. Thus the results are presented according to severity, from cannot manufacture to fully okay, with opportunities to improve yield in the yellow zone between. For example, it could be that the yellow results are okay for the prototype manufacturer, but would be a barrier to successful ramp to volume, so the application of the rules enables the designer to manage the progress of his product all the way to volume production, in fact, the full NPI lifecycle. So let's see Valor DFM technology running concurrently with PCB design. At this point I will hand over to my colleague Sangeeta to demonstrate Valor NPI running alongside PCB layout, a flow that can apply to all leading PCB design tools in the market today.
Thanks, Julian. I will now demonstrate how DFM analysis can be run concurrently by the layout engineer. Issues found can be reviewed and corrected in the layout tool. Prior to running any DFM analysis on the design, the netlist integrity is verified using the netlist analyzer. Designer-defined CAD nets are verified against the actual copper nets. This helps find broken nets and shorts, thereby avoiding errors in design that might result in non-functional boards. Fabrication checks are now run on the netlist validated design using the DFM rules that have been prepared by the NPI engineer. The issues can be reviewed within the manufacturing risk assessment interface and concurrently fixed in the layout tool. Now we will explore some of the fabrication issues. Stubs can be potential cause of signal performance or EMI issue on board. It is better to find these problems before handoff to manufacturing and not after the PCB is manufactured. cross-probing back to Layout tool to review and fix the problems. Here is an example of slevers. Laminate slever can cause material to detach during photo imaging, leading to risk of open circuits and low yield. The slevers are removed by concurrent editing in Layout tool. Problem of silkscreen ink on via. Silkscreen should never be applied on holes since it will be unreadable and adversely affect the assembly process. This issue is corrected in the layout by moving the silkscreen away from the holes. Here we see an issue of pad to circuit spacing that can cause incomplete etching and low yield. The spacing issue is cleared by moving the line in the Layout tool. Another spacing issue here that can cause incomplete etching and low yield, also cleared by adding more space between these two lines. Traces that are less than the threshold width can cause poor performance and can also lead to open circuits during manufacturing. Isolated features like these long and narrow conductors need to be modified to a larger width to eliminate this issue in the layout. A wide trace connected to a narrow pad may cause solder starvation on the pad. This difference in copper width will lead to uneven reflow process that will cause tombstoning. Reduced spoke width. The negative plane split creates a smaller spoke. This needs to be corrected by the designer either by editing the thermal pad stack or by adjusting the split plane. Here we see another sleeve on the power plane which can cause material to detach during photo imaging. This also needs to be corrected by the designer either by modifying the pad stack or by modifying the via. Disconnected copper areas like these with no electrical connectivity will serve no purpose and can cause flaking. These through-hole pins here connected directly to a plane without a thermal will cause improper solder joint due to heat dissipation. These direct connections are replaced with thermals in the layout. Here is a solder mask issue. Traces that pass too close to a pad need to be fully covered by mask to avoid solder bridging between trace and pad during assembly processes. This issue is corrected in the layout by the designer and now we see enough space between this trace and pad. With Valor DFM technology, the PCB designer can achieve a high level of DFM compliance before handing off to the NPI team. Back to you, Julian.
Thanks, Sangeeta. In summary, you have seen how the Valor DFM technology running alongside a designer's desktop offers a range of analysis checks that deliver high value and where problems can be fixed easily within the layout system during the design process, as opposed to waiting for the NPI team to report the problems after the design is complete. The DFM rules are managed on the design network by the NPI specialist for the benefit of all the PCB layout engineers. Integrating DFM into the design process, but without calling for the layout people to suddenly become experts in manufacturing process rules. It all connects to the emerging trend in electronics design to concentrate more functionality on the desktop of the engineer designer. In the end, it is much better to find and fix DFM problems at source rather than wait for the NPI team to find them later at greater cost in time and money. Let's now look at the next stage in the Lean NPI flow, which uses the full scope of the DFM analysis and product modeling capabilities of Valor NPI in the hands of the NPI or manufacturing documentation engineer on the design side. Before handing off to the manufacturers, and to fully take advantage of the Lean NPI left shift opportunity, your product design should be fully DFM validated, including using the Valor Parts Library to verify that all component supply chain data in the bill of materials and approved vendors list is correct and compatible with the PCB layout. Beyond that, the product model can be completed with a wealth of embedded intelligence to enable your fabricators and assemblers to drive their manufacturing process preparation in a highly automated way, whilst at the same time simplifying the product model configuration and version control tasks on your side. Once again, I hand off to Sangeeta to demonstrate the next product level NPI stages of the flow.
Thanks, Julian. In the product level NPI stage, the NPI engineer adds more manufacturing process definitions for running the assembly and test analysis, and then uses those results to add more intelligence to the product model before handoff to process preparation. In Valor NPI, the list of parts is accessed, then all the purchasable parts that may be used by the manufacturers is accessed, and the package and pin models are imported automatically from the Valor parts library. We see here all the package types and lead forms that will connect with the DFM rules to be applied. This information will be used automatically when selecting the correct rules to apply to the component analysis. Here we see the difference between the CAD library representation of a part and the Valor parts library representation, including precise outline and the pin contact area on the copper pads of a PCB. With this pin information superimposed on the copper pad and the relevant rules of the manufacturing process, a full and efficient analysis of the solder joints is made possible. For each design library part, there can be multiple commercial alternatives. These alternatives can often have small but significant differences in dimensions between them, which necessitate us to verify all possible component choices so as to ensure that they all conform to the manufacturing process and thus allowing full flexibility of component choice in manufacturing. Valor NPI analyzes all combinations of alternative parts and their impact on the manufacturability of your design. For example, here is a mismatch between component pins and the LAN pattern. We can see how this particular alternative does not fit satisfactorily onto the LAN pattern. This problem is rectified either by cross-probing back to layout and modifying the LAN pattern, or another suitable part should be found for the AVL. All combinations of supply chain parts are verified, so giving your manufacturers maximum flexibility when procuring materials. Here is a component-to-component spacing issue that illustrates the need to verify all combinations of supply chain parts. As we can see here, between different vendor parts, the component spacing can vary significantly, and these need to be caught beforehand to avoid costly revision spins. The revision spins can either involve changing the design or changing the AVL. It is better to find and fix now before committing to the purchasing of materials. Valor NPI analysis checks not only for assembly process compatibility but also your ability to gain access to all test points for maximum test coverage. Here we see an issue of a test point under the body of a component that makes it inaccessible by the probe. This test point needs to be moved away from this component body so as to make it accessible. Thus, manufacturability is optimized by fixing the problems either in the layout or in the master parts library or AVL, all as early as possible in the product life cycle for minimum revision spins and minimum time and cost impact during the NPI phase. Now that the PCB has been fully DFM validated, the NPI engineer can switch to preparing the complete product model for manufacturing to achieve maximum automation and accuracy in the later process NPI stages of the flow. What we are seeing now is the layer stackup information as brought in from the layout tool. ODB++ product model consists of the complete layer stackup information, including the various drill layers, their drill spans, and route information. There is scope to add further layer attributes like thickness of material, copper weight, etc., if this information has not been added already. The layer stackup information contained in ODB++ format eliminates need for stackup drawings and fabrication notes. In Drill Tools Manager, drills are listed by layer, grouped according to type and size. With all these information entered here, there is no real need anymore for a drill drawing since all the information normally held in a drill drawing is now stored as part of the manufacturing level product model in ODB++ format. As the DFM analysis and review is complete, those results also get automatically populated into the product model summary. And the NPI engineer can add even more information to the product model, further reducing the need for drawings and documents and potential of human error. For example, additional information about the thickness of the PCB and how it is measured. So, we see a lot of useful information that is normally seen in drawings and documents, but here it is stored as structured data that is part of the manufacturing level product model. Back to you, Julian.
Thanks, Sangeeta. We have just validated that the supply chain data in the AVL or Master Parts List is compatible with the product design and vice versa. The manufacturers have maximum flexibility in their materials procurement, and you have minimized the chances of late-stage engineering or AVL changes after the product gets into manufacturing. Your product design has been verified against all intended fabrication, assembly, and test process rules, and we are ready to compile the final manufacturing product model data ready for handoff to process preparation. The last step in preparing the product model for handoff to manufacturing is the assembly panel. This is the exact definition of what the fabricator delivers to the assembly manufacturer for processing down his assembly lines. Sangeeta, over to you to take us through this last stage of product level NPI.
Thanks, Julian. Now we will see assembly panel designing functionality in Valor NPI. The engineer selects the design and creates the assembly panel. The step and repeat configuration is defined and rotation is defined, after which a rapid DFM analysis is performed to ensure there is nothing wrong with this configuration before proceeding further. But in this case, we discover a DFM violation between two components that protrude outside the PCB profiles. By adjusting the step and repeat data, this problem is designed out of the panel. Now, the detail of the routing and V-score is defined. Fiducials are added with their attributes. Then tooling holes are added. Any text that is required can also be added into the panel at this stage, and then copper balancing is added according to preset rules. When all is defined, a final complete DFM analysis is then run on this final product model. And when all is confirmed as OK, it can be saved and exported and handed off to manufacturing.
What you have just seen illustrates how, by building the assembly panel in data, the need for the assembly panel drawing has been eliminated. No need for the fabricator to read the drawing, enter the data and reconstruct the panel, or engage in clarification and sign-off cycles. In the end, it is all about you, the design authority, fully controlling the definition of what will be manufactured by all of your manufacturing suppliers. We have now covered the product NPI flow, starting with DFM verification, running concurrently with your PCB layout system, through to comprehensive product modeling and verification, bringing us to the point where we are ready for handoff to the process NPI phase, where the execution-ready manufacturing processes will be generated for fabrication, assembly and test. Instead of an assembly panel drawing, we have a complete model of the assembly panel in data. Instead of a parts list and assembly drawing, we have all the components data, their attributes, positions and rotations defined in the data. The drill drawing is made obsolete by the drill tools data that is embedded. Fabrication notes, typically found on the fabrication drawing, is covered by feature attributes defining requirements such as surface finish and controlled impedance features, together with the summary data. The stack-up drawing data is included in the ODB++, shown here with examples of the dielectric requirements, including bulk resistivity and loss tangent for the dielectric layers and the copper weights for the conductive layers. When a complete product NPI process has been carried out, there is much more to the ODB++ than being an alternative to Gerber. Instead, it delivers a complete definition of what has to be manufactured, including all the information traditionally carried in paper or PDF documents, but now integrated into the structured data ready for immediate and automatic use by the next software tools in the flow. ODB++ is an open standard that is available to the PCB design and manufacturing market worldwide. Estimates indicate that over 1 million PCB designs have been processed into manufacturing using ODB++ since its introduction, giving ample proof of the format's ability to meet the rigorous demands of PCB global mass manufacturing. But to be of practical significance in the NPI workflows of the industry, such a format specification must achieve widespread adoption by all major software tools providers who are active at the interface between PCB design and manufacturing. The ODB++ Solutions Alliance includes all the major PCB design and NPI tools providers, all of whom receive the technical support necessary to provide an industrial-grade ODB++ interface as the format continues to evolve according to the demands of emerging technologies. The Alliance also provides a wide range of relevant content and software utilities for the benefit not only of the partners, but also the thousands of individual members who may be designers, NPI, or supply chain engineers. Membership is free and all are welcome. The ODB++ community continues to expand. But how can you be sure that the ODB++ data is really optimal for getting your product manufactured? Well, take a look at what the manufacturing process engineers do with it. First, we will take a look at how a leading PCB fabrication tooling system, such as InCam from Frontline, runs when starting with a fully prepared ODB++ data package. Here you see the user interface in InCam, where we start by loading the ODB++ data into the database. To begin with, you immediately see that there is the single-step version of the PCB and also the assembly panel. The assembly panel is there in its complete form, exactly as defined earlier by the product NPI engineer. A closer look at the layers and matrix structure shows that no aspect of the product model has been lost in the handoff to manufacturing. The route profile and V-scoring data is there, ready for conversion into process-compensated machine programs at a later stage, as is the drilling data, with all the information included for automatic generation of right first-time drill programs. Every drill hole data object carries the attributes about whether it is plated or unplated, whether it is a via or a through hole, plus the required final plated hole size and tolerance. The summary data is there in the database of the CAM system, ready for use by the engineering software, much better than being stuck as a statement on a piece of paper. Here we see overall thickness data and further multi-layer stack-up information. Surface finish definitions are defined and can be highlighted immediately for use in the tooling generation process, as can controlled impedance features. The process engineering specialist will always want to run his own DFM analysis, taking advantage of the intelligence in the ODB++ data, so as to validate manufacturability, but also to maintain the rules according to the actual manufacturing processes running in the factory. These automated stages take us quickly to the generation of the manufacturing process data itself. Here we see the creation of the panel that will go through the fabrication process. Notice that the most efficient material utilization in fabrication for this particular fabricator is achieved by placing 4 assembly panels into the fabrication panel. All that remains then is to generate the various machine programs for the manufacturing processes, taking full advantage of all the embedded intelligence in the database. Now, let's see ODB++ supporting the assembly and test stage of Process NPI. As before, the first step is to import the ODB++ product model, where you see the layers of the PCB relevant to assembly and test, with all layers stored in the database. All the rich component data is there, together with the embedded netlist. Bill of materials is according to what has already been integrated and verified. The assembly panel is there exactly as it has been fabricated. For example, the fiducials are recognized. The routing and V-scoring is there for singulation programming. The first stage of Process NPI is to define how the product will be assembled with allocation of parts to the different assembly processes. Straight to machine programming, supported by machine-level library data and the VPL. The solder stencil is generated as part of the process, derived from the process and product models. The output is then made to the stencil manufacturer. For the test process, first the test files are confirmed according to the tester selected, verified, and then exported as a machine-ready test program. Lastly, the moment has arrived when it is relevant to generate process documentation for the factory floor. The rich product and process models enable automatic generation of the correct documents for the selected process. Altogether, a complete execution-ready manufacturing process. That brings the Lean NPI webinar to a conclusion. Today we have shown how, in contrast to the traditional NPI flow that is characterized by cost increases, quality risks and delays, a far better Lean NPI flow is available based on proven Valor technologies. The Lean NPI flow starts with maximizing the benefit of left-shifting DFM onto the designer's desktop, running concurrently with all well-known PCB layout tools, enabling the designer to minimize manufacturing-related revision spins at source, but without having to be a manufacturing expert. Following that is a comprehensive product NPI operation based on the Valor NPI platform that completes the left shifting of all aspects of DFM and provides an efficient handoff to Process NPI for right first time introduction to manufacturing, fast ramp to volume, and with maximum flexibility in the supply chain between all your fabrication and assembly suppliers. As you will have seen, Lean NPI is a flow-based solution for a business process that extends across design and outsourced manufacturing operations. Every participant in the flow can state that it is better for me, but also better for you, my partners in the process. We hope this webinar has been informative. We invite you to look more deeply at the Lean NPI solution, to consider how it could benefit your design and NPI operations. The best place to start is by evaluating the Valor NPI technology for yourself using the virtual lab that is available at the web address shown here. You will be able to run the Valor NPI application remotely over the web to evaluate the functions of DFM validation, manufacturing product modeling, and ODB++ output more deeply than is possible in a short webinar such as this. Thank you for your attention.